Yes, students, the topic is Hessenbergs uncertainty principle. So, according to classical theory, the position, momentum of a particle can be determined precisely when the particle is in motion. Classical physics, what it says is, whenever a particle is in motion, its position, momentum, velocity values can be determined precisely if the earlier values, the previous values are known. But it is not so in case of the particles which are associated with waves when they are in motion. So according to quantum theory, a moving particle is associated with a wave. In such a case, it is not possible to determine the values of velocity or momentum or position precisely as it is explained in classical theory. This uncertainty in the measurement of position, momentum, etc. was explained by Hessenberg using the principle called Hessenberg's uncertainty principle. See here, Hessenberg's uncertainty principle, what it says is, it is impossible to determine the values of the physical variables which make a pair precisely and simultaneously. The precise and simultaneous measurement of the values of the physical variables which make a pair is not possible. That's what Hessenberg's uncertainty principle states. See, for example, suppose we have a pair of physical variables, say position and momentum. These two make a pair of these are the physical variables which make a pair. Delta x, the position along x direction, delta px, component of momentum along x direction. According to Hessenberg's uncertainty principle, it is not possible to measure delta x and delta px or the position and momentum simultaneously with accuracy, with 100% accuracy. That means if delta x is measured accurately, there will be some error in the measurement of this px. If px is measured accurately, there will be some error in the measurement of the position. This is what Hessenberg's uncertainty principle says. And these three are the mathematical forms of Hessenberg's uncertainty principle applied to the three conservation laws. First one is law of conservation of linear momentum. Second one is conservation of angular momentum. Third one is conservation of energy. Hessenberg's principle is applied or it is written in the mathematical form like this. Here, conservation of momentum. Here, momentum and position, they make a pair of these physical variables, make a pair so that delta px into delta x is always greater than or equal to h bar by 2. Delta px, error in the measurement of momentum. Delta x, error in the measurement of position. What is h bar? H bar is h by 2 pi. Similarly, conservation of angular momentum. Here, delta L, error in the measurement of angular momentum. Delta theta, error in the measurement of angular position. So that delta L into delta theta is greater than or equal to h bar by 2. Conservation of energy. Delta E into delta T greater than or equal to h bar by 2. So the minimum error is equal to h bar by 2. The error may be h bar by 2 or more than that. This is Hessenberg's uncertainty principle. See, the position and momentum, they make a pair. Why error occurs? How the principle explains about the occurrence of the error like delta x and delta px. Why that error occurs? Let us consider a wave associated with a moving particle. Suppose that wave is, see, we have studied in the previous class about the matter wave. Moving particles are associated with the matter waves, and matter waves are always represented in terms of wave packet or group of waves. It's not a single wave, a group of waves or a wave packet represents the matter wave. So that in that wave packet, there is a probability of finding the particle somewhere in that wave packet. So we consider, see, the locating the position of the particle depends on the probability of finding the particle at the given point. At some point, probability of finding the particle is high, at some point it's very low. So here, Why the error occurs? To explain this, let us consider a wave associated with the wave packet associated with the moving particle. Let the wave packet be a narrow wave packet, a very small wave packet consisting of less number of waves. A very narrow wave packet consisting of less number of waves, many waves make a packet. So that in this case, lambda, the wavelength is small, less number of waves. So lambda is small here, very narrow wave packet, lambda is small. If lambda is small, then we define momentum of the wave, matter wave as h by lambda. Lambda is h by p or p is h by lambda. When lambda is small, wave will be more. If you consider the error in the measurement of the momentum, then since lambda is small, delta px, error in the measurement of momentum will be more. And what about delta x? So in this case, delta x indicates the position. Since the wave packet is very narrow, finding the position or measuring the position of the particle is very easy. It can be done accurately. In this case, position can be measured, delta x can be measured, delta x will be small, error will be less. And the position can be measured accurately, whereas momentum cannot be measured accurately. Suppose the wave packet is a big wave packet containing more number of waves, say. A wide wave packet. In this case, lambda is large. Lambda large means what about momentum? Momentum will be less. So in this case, error in the measurement of momentum is less. But what about position? So you can find the particle anywhere in this region, anywhere in between these 2 points. So locating the particle is not that easy. So we cannot measure the position accurately in this case, but momentum can be measured. This is the momentum and position. They cannot be measured accurately. They cannot be measured simultaneously with accuracy. If you measure one component accurately, there will be error in the measurement of the other one. This is about Hessenbergs uncertainty principle. And this uncertainty principle, this theoretical prediction was experimentally again proved by Hessenberg itself using a thought experiment. He produced a thought experiment called gamma ray microscope experiment. It is the thought experiment used to verify or to prove this uncertainty principle proposed by himself. So it is a gamma ray microscope experiment. Gamma ray microscope. You know about the optical microscopes. Optical microscopes are the devices which are used to give a very or a resolved images of closely spaced objects. The resolved images of closely spaced objects. So there, the resolving power of that any optical microscope depends on lambda. So I have given the expression here. Resolving power is given by the formula. Actually, it is 2n sin theta by lambda. N is refractive index of the medium. The medium is air. N is 1. So that this resolving power of an optical microscope or a microscope in general, it is given by 2 sin theta by lambda. Theta is the semi-vertical angle made by the pole of the rays with the objective of that microscope. Lambda is the wavelength of the radiation used to illuminate the object. Thus, this equation says resolving power varies inversely as the wavelength. As lambda decreases, resolving power increases. Lambda less means resolving power is more. Gamma rays, they are going the shorter wavelength. The shortest wavelength is for gamma rays in the electromagnetic radiation. So, since lambda is very, very small for the gamma rays, the gamma ray microscope has got very high resolving power. And here in this microscope, gamma photons are used. Here at this point O, there is an electron. It is bombarded with a gamma photon. Consider a gamma photon of momentum P0. Initial momentum P0 is given by h by lambda naught. Initial momentum of the gamma photon. Gamma photon collides with the electron at this point. Compton effect takes place. The electron acquires some momentum, then gets scattered along this recoils. The electron recoils, and after losing some energy or some momentum, the gamma photon scatters. Let the scattered gamma photon be collected by the this objective of the optical microscope. This microscope. This is the objective of the microscope. The scattered gamma photon is collected by this objective or received by the object of the microscope, and here it is considered that scattered gamma photon scatters in a cone of rays OBA. In this region, it scatters with an angle of 2 theta and received by the objective of the microscope. The scattered gamma photon scatters with this angle 2 theta. It is confined to this cone of angle 2 theta and received by the objective of this microscope. Now here, see, the gamma photon is confined to this cone. It may scatter along OA or it may scatter along OB. So that it is confined in that cone, making an angle 2 theta. Now, if the momentum of the gamma photon scattered along OA, it is taken as P equal to h by lambda. The photon has got less momentum. The momentum is little less after scattering. Let it be h by lambda along OA. Similarly, if the photon scatters along OB, its momentum is also h by lambda given by P. Now, let us find out the components of these two momentum along x direction, along OX direction. Consider or find the components of these two momentum along OX. So, and here, let delta x be the error in the measurement of position, delta px error in the measurement of the momentum of the electron. Electron recoils in this direction. Delta x error in the measurement of position of the electron, delta px error in the measurement of momentum of the electron. Now, to find the x component of the scattered photon, x component of momentum of the photon which is scattered along OA is nothing but, let us find the x component. Actually, it scatters along OA, x component it is along OX. What's x component? It is P cosine component, P cos 90 minus theta. This angle is, this is theta, this is 90 minus theta. So the component will be along this direction is P cos 90 minus theta. Cos 90 minus theta is sin theta. So the component is P sin theta. X component of OA is P sin theta. Nothing. What is P? H by lambda. So this is H by lambda sin theta. Similarly, X component of this momentum, it is along this direction. But we need the component along OX, positive X direction. Again this is P cos 90 minus theta. Along this direction it is P cos 90 minus theta. It is P sin theta. Along this direction, so along OX it is minus P sin theta. It becomes, I have not written those things here, it becomes minus P sin theta. X component of this is along this direction, negative X direction, it is P cos 90 minus theta, P sin theta. So along OX, this direction is minus P sin theta, nothing but minus H by lambda sin theta. Now we got the X components of the momentum of the photon scattered in this direction along positive X direction. Now, here is the process. The photon hits the electron, transfers its momentum to the electron. Now, what is the momentum transferred to the electron by the photon? Momentum transferred to the electron by the photon along X direction. That's important. Initial momentum is P naught. X component of momentum, one is lambda h by lambda sin theta, so that the momentum of electron, see here I have written momentum transferred by the photon scattered along OA to the electron. Thus, if the photon scattered along this direction, the momentum transferred by that photon to the electron in this direction is given by P naught minus h by lambda sin theta. P naught minus P sin theta, it is P naught minus h by lambda sin theta. Similarly, momentum transferred by the photon scattered along OB. Momentum transferred by the photon to the electron scattered along OB. It is nothing but P naught minus h by lambda sin theta. the x component of this momentum, it is nothing but minus h by lambda sin theta. Therefore, momentum transferred by the photon scattered along this direction is given by P naught minus h by lambda sin theta. We get P naught plus h by lambda sin theta. Now, what's the net momentum? Now, we have the two momentum values along the same direction OX. So, what's the net momentum? Difference between the two. The net momentum of the electron. Net momentum transferred to the electron by the proton. Net momentum transferred to the electron by the proton. It is given by the difference between the two values. So, P naught plus h by lambda sin theta minus this value from this P naught 0 minus P naught 0. You get 2h sin theta by lambda. This is nothing but the net momentum taken as delta px. Net momentum is considered as delta px. So we got the expression for delta px 2h sin theta by lambda. Now about delta x. What is delta x? Position of the electron. Finding the position of the electron or measurement of the position of the electron. This is position of the electron. It is similar to the limit of resolution. Limit of resolution in case of the resolution of an optical microscope. What is limit of resolution? The smallest distance between the two objects for which the objects appear resolved. Smallest separation or distance between the two objects for which the objects appear just resolved is the limit of resolution. So, delta x is nothing but that limit of resolution, and limit of resolution is always reciprocal of the resolving power. Resolving power, reciprocal of the limit of resolution, or vice versa. So that the position nothing but limit of resolution delta x. Reciprocal of the resolving power x this one. So we get delta x as lambda by 2 sin theta. Now find out the product delta px into delta x. We get set this into this. 2 sin theta cancels, lambda cancels, remaining is h. From this, what we get is equal to h. Thus, the product of these two variables, delta px, delta x, from this experiment obtained as h equal to h. And more precisely, this value is approximated to h bar by 2. To be precise, the value should be greater than or equal to h bar by 2. Minimum is h bar by 2. This is how Hessenbergs uncertainty principle is. That expression is got experimentally using this long array microscope experiment. This is also called as a thought experiment. With this, I stop here. Let us continue the next class with the applications of Hessenbergs uncertainty principle.